Welcome to Introduction to RLC Circuits short course. In this short course, we will talk about resistors, inductors, and capacitors, and we will try to understand how they behave in DC and AC powered electric circuits. The goal of this short course is to give you a better theoretical understanding. In this regard, it's going to be purely mathematical. We will write down the equations for circuits. We will solve them using calculus or the methods used to solve differential equations and complex algebra. This short course is composed of 5 different sections. So in the first section, we will talk about RL and RC circuits powered by DC sources. In the next section, we will talk about RLC circuits powered by DC sources. In the third section, now we will have AC sources powering an RLC circuit. So in the fourth section, we will talk about phasors and complex representation of the circuit elements. In the last section, which is my favorite, we will talk about equivalency between mechanical systems and electric circuits. So in other words, what we will do in the end is that we will take a mechanical system and we will build an electric equivalent of that. So this will be so much fun. As I mentioned earlier, even if the name of this short course is Introduction to RLC Circuits, you are required to know calculus, differential equations, and complex algebra. If you do not know any of these topics, this short course is not for you. I would also like to remind you that my previous work, RLC Circuits, a comprehensive review, is also available on Patreon for Fusion members. The order of contents in that study, however, is a little bit different than the order of contents which will be presented in this short course. I highly recommend that you go through that study as well. We would highly appreciate if you support us on Patreon as well. Now we will start with the first section, RC and RL circuits powered by DC sources. Welcome to Introduction to RLC Circuits short course. This short course is the continuation of your Electricity and Magnetism class, so we will not talk about what a resistor is, what a capacitor is, what an inductor is, but rather we will talk about how these circuit elements behave in DC powered and AC powered electric circuits. So in the first section, we will talk about RL circuits and RC circuits powered by DC sources. We will first start our short course with RL circuits powered with a DC power source. So as you may all know from your Electricity and Magnetism class, the inductors don't like any change in the current. Okay? They built up some potential difference across their terminals if there is any change in the current, or in other words, magnetic flux through them, right? Initially, when I close the switch, so I close the switch when t is equal to 0. So when I close the switch, this inductor, the presence of this inductor, is not going to let the current run rapidly in the circuit. So the current is gradually increase. So without loss of generality, I can say that the current in the circuit when time t is equal to 0 is equal to 0. And this is my initial condition for this type of a circuit. Okay, so when t is equal to 0, I close the switch and the current is running when time t is equal to t here. Okay, so at any time t, the current will be I. So if I'm going with the current like that, the potential will drop across the resistor. So if I assume the current is increasing in that direction, there will be a potential drop across the inductor as well. So if I write this down as an equation, I'll have the potential drop across the resistor. I assume it's an ohmic resistor, and I'll have minus L di over dt. Very good. And then my potential is going to increase when I cross this power source, and it's a DC one, so V0 is a constant. I close the loop, so they all add up to 0. Okay, this is good. So I can multiply everything with a minus sign. This becomes plus here. So this becomes minus, of course. And I can put V naught on the other side. So this becomes just equal. Okay, at this time, if I divide everything by R, what I see is something interesting. Let's check the units. I have current here. I have current over time times L over R, and I have the units of current here. So L over R is nothing but some time parameter, right? I'll call it tau L. L over R. So this is how I've defined the time constant for an RL circuit. Okay, so I would like to solve for I then, right? This is what I want to do. So I can simply write this as dIL, di over dt is equal to, so this is V naught over R minus I, right? So if I equate the denominators here, this becomes just I times R. Okay, very good. So if I put all the constants on one side and all the I terms on one side, I'll have di over V naught minus IR times R is equal to dt over the time constant tau L. At this point, I can actually do the integration, right? Can integrate both sides. I can use integration variables, so I can use I prime here and t prime here. So when t prime is equal to 0, the initial condition here tells me that I prime is simply equal to 0. So when t prime is equal to t, I prime would be I. So I'll have I as a function of time t. Okay? So now I can do U substitution here. With me V naught minus I prime R. So du is simply equal to minus R di prime. Okay? So now this integral becomes, the limits change of course. So when I prime is equal to 0, this is V naught, and this is V naught minus IR. So minus du over u, which is equal to, integrating this side is easy, it's going to be t over tau L. So I can put the minus sign on this side, and this is nothing but the Ln function, right? So I'll have, continue from here, Ln V naught minus IR over V naught is simply equal to minus t over tau L. Okay, then V naught minus IR is equal to V naught times e to the minus t over tau L. And if I solve for I, what I get is V naught over R 1 minus e to the minus t over tau L. Okay, this is very good. So this is the answer for I as a function of time t for an RL circuit powered by a DC source. Quite nice, right? So let's check the limits. So when t goes to 0, when t is equal to 0, I goes to 0, as suggested here. When t goes to infinity, in other words, in steady state. We will use this term a lot in this course, steady state, which means when time t goes to infinity. Okay? So I tends to V naught over R. Okay, let's write down those limits. So when time t is equal to 0, the current is equal to 0. When time t goes to infinity, the current becomes V naught over R. So if I plot this, I, as a function of time t, what I see is initially it is 0, and finally it reaches an asymptotic value, which is V naught over R. Okay, so if I wait long enough, the current in the circuit turns out to be V naught over R. Wait, what is V naught over R? I have R here, this is V naught. It's as if there is no any inductor in the circuit. This is quite nice. So when t is equal to 0, there is no current in the circuit, meaning that the inductor behaves like open. So it means as if there is no any closed loop here. So there will be no way for the current to run. However, if I wait long enough, the inductor behaves like short. So this is open, this is short. So these are the typical behaviors of an inductor in a DC circuit. So far we have talked about RL circuits powered by a DC source where we had a resistor and an inductor. So initially the current was 0 due to the presence of the inductor. So as we let the time go, the current increases and it approaches an asymptotic value, which is V0 over R. So this result suggested that when time t is equal to 0, the inductor behaves like an open in the circuit. Okay? So there will be no current running through this branch. When time t goes to infinity, the current approaches a constant value, so there will be no time rate of change of the current, so there will be no potential built up across the inductor. So that's why the current becomes V0 over R, and it seems as if there is no any inductor in the circuit anymore, or in other words, it's as if it's replaced with a piece of wire. We just call it short. So now the next example that we will discuss is the RC circuits, where now we have a resistor and a capacitor. When time t is equal to 0, we close the switch and we let the current run. And we know that the capacitor is initially uncharged. So our initial condition is when time t is equal to 0, Q on the capacitor is simply equal to 0. This is good. So as the current runs like this, it charges this capacitor. Okay. So before we solve this problem, what we can expect is that initially, since there is no charge on the capacitor, the potential across the capacitor should be equal to 0. As time t runs, the capacitor is going to be charged. Okay? So this side becomes positively charged and this side becomes negatively charged. This is good. So when this capacitor is fully charged, we expect that there will be no current in the circuit. So it will not be possible to charge this capacitor any further. Okay? So when time t goes to infinity, we expect that this current tends to 0. And this is what we should see in our results. Okay, so let's get started. So when I is running like this, the potential drop across the resistor is going to be like this. Side B positive, this side would be negative. So if I'm moving with the current, there will be a potential drop across the resistor. Then I will have a potential drop across the capacitor. Then I'll have a potential increase here, which is going to be V0. And this is going to be 0 as usual. So if I multiply with a minus sign as usual, this becomes positive, this becomes minus. I can put V0 on the other side, this becomes equal here. This is good. So now I can divide everything with R. So this becomes RC, this becomes R. This is also good. So now the problem is I have I and Q. So they are both functions of time. But are they related? Okay. Current is time rate of change of the charge, right? So the charge here on the capacitor is actually provided by this current. So this current is feeding this capacitor. So then I is simply equal to dq over dt. Okay? So here instead of I can write dq over dt. Let's check the units. like we did before, this is Q over T, which has the units of current, Q over RC. So RC should have the units of time, right? So we will define the time constant for an RC circuit as R times C. So this is a typical measure of how fast this capacitor is going to be charged, right? So if RC time constant is large, it takes longer time for this capacitor to be fully charged, okay? If RC time constant is small, it charges so fast, okay? Physically, it also makes sense, right? If R is large, right, R limits the current, right? So there will be less current, so it will take more time for this capacitor to be charged. If C is large, okay, it can accumulate a lot of charge because Q is equal to C times V. This is the capacitor equation, right? So if C is large, it can hold a lot of charge on itself. So it takes longer time to be fully charged. So physically, this time constant really makes sense. Okay, so now I can write this equation as dq over dt is simply equal to V naught over R minus Q over RC. Here, I will equate the denominator, so this will be C times V naught minus Q over RC. This is good. Let's put all the Q's on one side, all the constants on the other side. So you'll have dq over C V naught minus Q is equal to dt over RC. At this point, I'll just call this the time constant, tau C. Okay? And we are ready to integrate. Okay. So let's call it Q prime, T prime. Integrate. When T is equal to 0, okay, my initial condition is right here. So Q must be equal to 0. When T prime is equal to T, the charge is going to be Q. So when I solve these two integrals, I'll get Q as a function of time T. Okay? So the left-hand side simply gives me minus ln C V naught minus Q divided by C times V naught, right? This is the lower limit. So I put Q to be 0 here, the lower limit. So this will be equal to T over RC, or tau C. So I can put the minus sign here. And I can get rid of this ln function. So C V naught minus Q is equal to C times V naught e to the minus T over tau C. Okay. Then I can solve for Q. Q of T is equal to C times V naught, right? C times V. Then I'll have 1 minus e to the minus T over the time constant tau C. Okay. So this is how Q changes as a function of time. Okay. Since the current is related to that, which is the first derivative, right? Can find the first derivative here, I of t, simply equal to C V naught, the derivative of 1 is 0, I'll have minus C times V naught times minus 1 over RC, so C's cancel, I'll get V naught over R, the minuses also cancel, and I'll have minus e to the minus T over tau C, which is also RC, right? So this is how the current changes in the circuit. Okay, so if I plot Q as a function of time t, what I see is it approaches a value C times V naught. So as you see, if I wait long enough, okay, the capacitor is going to be fully charged, and the potential drop across the capacitor would be the same as the potential drop across the power source, DC power source. This is good. So if I plot I versus t, what I see is it simply decays like that. So the value here is simply V naught over R. When t is equal to 0, I is equal to V naught over R. So it's as if there is no any capacitor in the circuit when t is equal to 0. So there is no any reactance of the capacitor initially. So Unlike inductors, right, when t is equal to 0, capacitor behaves like a short. But if we wait long enough, right, the current goes to 0 here. When we wait long enough, the capacitor behaves like an open. So this is the main distinction between an inductor and a capacitor in a DC circuit. In the last board, we talked about an RC circuit powered by a DC source. Initially, we assumed that the charge on the capacitor is 0, and we show that the charge on the capacitor gradually increases, while the current in the circuit decreases. So if we wait long enough, the capacitor is fully charged. That's why we also call this circuit a charging circuit. We are charging a capacitor. So when the capacitor is fully charged, the charge on the capacitor takes the value C times V naught. So in other words, the potential drop provided by the DC source is going to be seen across the capacitor only. So we would expect to have 0 potential drop across the resistor if we wait long enough. And the current versus time graph also confirms that, because if we wait long enough, the current in the circuit goes to 0. This is just an exponential decay. So in short, what we can conclude is that when time t is equal to 0, or in other words, when capacitor is uncharged, it behaves like a short. So it can be replaced with a piece of wire with 0 resistance. So if we wait long enough, when the capacitor is fully charged, it behaves like an open. So there will be no any closed loop. Then the current tends to 0, of course. In this last example, we will actually assume that the capacitor is initially charged and there is no any external DC source, and the charge is going to be lost through the resistor. So this is an example of a discharging circuit. So of course, when t is equal to 0, we close the switch, and initially, so Q when t is equal to 0 is simply equal to Q naught. So without loss of generality, you can always assume a direction for the current. So let's assume I is running like that at any given time t. So it's feeding the positive terminal. So I is again equal to dq over dt. Okay? If I write down the closed loop equations, so if I is running like that, the potential drop across the resistor is going to be like this. So I'll go from positive to negative, so minus IR is going to be the potential drop across the resistor, minus Q over C is going to be the potential drop across the capacitor, and there's nothing else, so this is equal to 0. So I can multiply everything with minus, this becomes plus, and instead of I can write dq over dt. So the first term becomes R times dq over dt. So I can divide everything by R, so this becomes RC, or the time constant, tau C, in an RC circuit. So this is an easy equation. So dq over q becomes minus dt over tau C. Here we need to be careful because the initial condition is a little bit different, right? So initially there is a charge on the capacitor. So this is going to be Q naught and this is going to be Q. So let's call it Q prime, this is D prime. The integral is going to be 0 to T. So this gives me ln Q over Q naught is equal to minus T over tau C, right? If I solve for Q, this becomes Q is equal to Q naught e to the minus T over tau C. So in this case, the Q also decays exponentially, right? So this is a typical discharging mechanism. Okay? So if I calculate I, what I see is I simply take the time derivative here. So this is minus 1 over RC, right? So this becomes minus Q naught over RC e to the minus T over tau C. So this is how the current changes with time. Why do I have a minus sign? Any ideas? Okay, this tells me that the direction I picked for the current is wrong. So as you may all guess, since this side is positive, this is negative, the current is going to run through like that, right? In the counterclockwise direction. But I assumed I is going in that direction. So this is how I used to write down the equations, but in the end, I turned out to be negative, meaning that it's actually running in the opposite direction. So it doesn't really change the physics. So it actually corrects the direction here. So if I plot Q as a function of time t, so it's going to be a decay like that. If I plot I versus t, it is also a decay. So let's plot the absolute value of I. So in the end, if I wait long enough, the current in this circuit would be 0, and there will be no charge on the capacitor plates. It's going to be completely discharged. So in this first section, what we did was we studied RL circuits, powered by a DC source, and then we looked at an RC circuit where we were charging a capacitor using a DC source. In this last example, we looked at an RC circuit where there is no any external DC source and this capacitor is initially charged, and we looked at how it loses its charge with time. Now we will complete the section 1 of Introduction to RLC Circuits by solving some examples, and we'll make all these concepts clear. Before we complete section 1 of the Introduction to RLC Circuits short course, we would like to solve some examples so that the concepts we have talked so far will be a lot clearer. We have 3 questions that we would like to solve. In the first question, we have 2 RC circuits where we actually charge these 2 capacitors C1 and C2. Based on this current versus time graphs, we would like to compare R1 and R2 values and C1 and C2 values. Initially, both capacitors are uncharged, and when time t is equal to 0, we close these 2 switches. Good. So if I look at this I versus time graph, when t is equal to 0, both capacitors are uncharged, so they can be replaced with a short, right? So the current in the circuit, in the first circuit, would be just equal to V0 over R1. So I can simply write it down. I1 0 is equal to V0 over R1. And I2 0 would be equal to V0 over R2. From the I versus time graphs, what I see is when time t is equal to 0, these 2 currents have the same value. So V0 over R1 must be equal to V0 over R2. This suggests that R1 must be equal to R2. So these 2 resistances should have the same value. For part B, what I see from this I versus time graphs is that for the first circuit, it takes longer time for this current to decay. In other words, for the first circuit, time constant, RC time constant, should be larger. Okay, so what I can say is R1 C1 must be larger than R2 C2. So from part A, I know that R1 is equal to R2, then I can conclude that C1 must be larger than C2. If you look at the next problem, we have a circuit which includes resistors and inductors. So in the question, they ask us what is the current when time t is equal to 0. So at time t is equal to 0, we simply close the switch. As we know from the properties of the inductors, as soon as we close the switch, there will be a huge potential drop across the inductors, and they behave like open. So if I want to replot this, so wherever I see an inductor, I'll replace it with an open. So there is R1 here, and There's also R2 here, right? So what do I see? Do I see any closed loops? No. So the current time t is equal to 0 must be equal to 0. Okay? So if they asked us what is the current when time t goes to infinity, so let's find that one too. So what is the current when time goes to infinity? So when time goes to infinity, I can replace, we reach the steady state, so we can replace these inductors with piece of wires, right? They will behave as shorts. So we'll have a short here, R1 here, right? And another short here and R2. So R1 and R2. As you see, we have a short circuit here, so the current is going to run through like that. So it's going to bypass R1. So it's going to run through R2 only. So this will be the direction of the current. So the current, when time goes to infinity, we will only have R2 in the circuit. So 5 ohms, 20 volts to 20 divided by 5 is simply equal to 4 amps. So if you wait long enough, the main branch current here would be just 4 amps and it's going to go through R2 only. Okay. So let's look at this last example here. We have a circuit with resistors and capacitors, and they ask us what is the charge on each capacitor in steady state. So if we wait long enough, okay, what will happen to the charge on these capacitors? So if we wait long enough, the capacitors are going to be fully charged and they will behave as opens, right? So if I want to draw this, so I will have R1 here. So replace C1 with an open. So there is a battery here, another resistor, and I'll have another open here. I'll have a 10 volt battery. We need to be really careful with the polarities here. Okay, and then I'll have another resistor here. Okay, I call it R3, this is R2. Okay. So we do not see any closed loops here, so there will be no current running through any of these branches. So if you have a problem, if you have a circuit like that, the best way to analyze it is to choose a reference. So let's choose a reference for the potential. So let's choose this point to be 0 volts. You can choose any point you like. So since there is no any current running through resistors, so this point would be just 0 volts, and this is also 0 volts. So there will be no potential drop here. So when I cross here, so this is a 10 volt potential source. This side is positive, the downside is negative. When I go this way, this point will be minus 10 volts. And here is going to be minus 10, this is going to be minus 10 volts. Good. When I go this way, this point will be minus 20 volts. So that the potential difference here would be 20. And this point must be minus 20, and this point is also minus 20 volts. Okay. So when I look at C1, the potential drop across C1 would be 20 volts. So this side would be positive. So this side would be positively charged, this side would be negatively charged. For the C2, the potential difference would be 10 volts. And minus 10 is larger than minus 20. This side would be positively charged, this side would be negatively charged. So V1 is equal to 20 volts. V2 will be equal to 10 volts. So this suggests that, so Q is equal to C times V, right? So Q1 would be equal to, C1 is 10 microfarads, 10 times 20 is 200. So this is 200 microcoulombs. And Q2 would be equal to 10 times 20. So this is also 200 microcoulombs. This completes the first section of Introduction to RLC Circuits short course. I hope you all liked it. If you have any questions, please ask them in the comments. I look forward to seeing you all in the next section. Have a good day. See you later.